Oh, good morning. Good morning, everyone. Welcome to our pre-lab, our lecture. Today we are going to go through the chapter on naming and writing the chemical formulas for inorganic compounds. If you are taking the course this semester, or if you took the course before, this falls under the chapter on language of chemistry for those who are using Cowin text. All right, it is pretty straightforward. Last night, I thought I shared the resources you can use to complete the assignment or the data sheet. Nevertheless, I will quickly go through, overview on naming of inorganic compounds and writing their chemical formulas. Let me share my screen here and use the whiteboard uh, to write some notes regarding the topic or the title of the experiment today. Now, as far as the inorganic compounds, when we say inorganic compounds, all right, inorganic compounds are compounds which do not have hydrogen or element carbon, except for carbonate, of course, and cyanide. Most inorganic compounds they don't have element carbon and hydrogen, except in organic compounds you will see with element carbon is carbonate, which this is polyatomic ion, or cyanide, which is these two are polyatomic ion. For most part, inorganic compounds, those are compounds which do not contain element carbon and hydrogen. You're gonna see that in hydrocarbons. There is a branch of chemistry which deals with compounds which only contain element carbon and hydrogen. We call those organic chemistry. So the flowchart for inorganic compounds, you have to be able to break down the inorganic compounds into these classes. Inorganic compounds can either be ionic, all right, ionic compounds, it can be molecular compounds, or it can be acids right here. Acids. These are the classes of compounds which breaking down starting from the top. Organic compounds can be either organic, ionic, molecular, and acid. Ionic compounds can further be subdivided into what we call binary ionic compounds, or ternary ionic compounds. These are just binary molecular compounds, and these could be also subdivided into what we call binary acid. All right, and here is right here in that, because of the space, we have what we call oxy acid. So I see here there is one. Oh, sorry about that. We have 1, 2, 3, 4, and 5. 5 classes of inorganic compounds, and there is a rules for naming them and writing their chemical formulas. I'm gonna start from here, all right? I'm gonna start from here all the way to oxalic acid, and this is what will help you in completing today's assignment. This is the flowchart. You can generate your own. You should be able to classify a compound as either binary or ternary or oxalic acid or binary acid or binary molecular compounds given the chemical formula. Once I'm done with that, you should be in that position. I know some of you already know. Let me start by, before we look at binary, before we start with this, let me number them so that we don't lose track of where we are. Let me number them as 1. All right, I should have used this 1. This is what I wanted to say. 1, 2, 3, 4, and 5. So there are 5 classes of compound we're gonna look at. Those are the 5. 1, binary ionic. 2, ternary ionic compounds. 3, binary molecular compounds. 4, binary acids, and 5, oxalic acid. Before we look at the first one, we have what we call ions, all right? Ions are basically charged. We call these charged what? Particles. And charged particles can either be what? Can either be cations, can either be anions, all right? Or it can be polyatomic ions, polyatomic ions. In order to understand, all right, in order to understand how to name and write the chemical formulas for ionic compounds, you need to understand the anatomy of, ions. Ions are charged particles and can either be cation, anion, or polyatomic ion. How do I differentiate between all these 3 types of ions? Cations are positively charged, that's one thing, all right, positively charged. Anions are negatively charged, all right, they are negatively charged. Examples are Na positive, Ca2 positive, Al3 positive, all right. I can have Fe2 positive or Fe3 positive. All these are cations, all right? And we have positive, negatively charged particles we call anions, and this includes such things as chloride, Cl negative, O2 negative, all right, NO, not NO, but N3 negative, N3 negative, like that. I didn't mean to have that as a subscript, but it should be superscript. 3. This is 3 right here. I meant to say this is 3. Polyatomic ions are a group of atoms which act as one. They are a group of atoms with overall charge, SO3, for example, with an overall charge of -2. This is poly, means many. It's a collection of atoms with an overall charge. PO4 with an overall charge of 3, all right? These are polyatomic ions. Let me just see if I can show you polyatomic ions. All right, I had polyatomic ions, not that. Yeah, polyatomic ions. If you look at this table, these are polyatomic ions. If you look at all of them, they have an overall charge. Overall charge is a collection of atoms which act as one with an overall charge. I will post this document on Canvas. You'll be using this to study. You don't need to memorize all of them. You'll be there's some common in your text. You'll use that. So, having said that, this one, polyatomic ions, all right? You need to memorize their names. But for, all right, for these two right here, all right, let me just show you these two right here. How do we keep track of the ionic charge? Predicting the ionic charge for cation and anion for main group elements, all right, predicting the what? Predicting ionic charge for mono atomic ions, use periodic table. All right, periodic table helps you to predict the ionic charge for main group elements. All right, note this is for what? For main group elements or representative elements. Main group or representative elements. These are the elements numbered with a letter and a number or Roman numeral with the letter A. For metals, all right, for metals, they lose valence electron. That means electrons in the outermost shell, and they form positive one if it is group one. So if it is one, group 1A, they'll form for metals. They'll form positive one. For 2A, they form positive 2. For 3A, metals, they form positive 3. When you get to group 4, we have lead, and lead can form positive 4 or positive 2. We have antimony, which can form positive 12, positive 3. You got to remember. For non-metals, they gain electrons. And losing has to do with remaining with 8 valence electron in the outermost shell. So if it is past 4, they're gonna gain electrons to get to 8. So if I have 1 all the way to 8 here, the losing and gaining has to do with the octet rule. That means ending with 8 electrons in the outermost shell. Lithium has 3 electrons. If it loses 1 electron, it will form Li positive like that, and remain with 2 electrons, which look like group 8 helium. Now, for non-metals, they gain they gain electrons to complete their valence shell with 8 electrons. Nitrogen is in group 5A, and it needs 3 more electrons to get to 8. Oxygen is in 6A, all right, and it needs 2 more to get to 8. Now, 7A, such as fluorine, will form -1, all group 7A. That's how you predict the ionic charge for these two class of compounds. There's a pattern here. And most chemistry concept is all about pattern. You don't need to memorize that always gonna be positive 1, always gonna be positive 3, or it's gonna be a total on you. It's just using the periodic table, and given the periodic table, you should be able to predict the ionic charge for cations and for anions. For the transition metals, the d block elements, if you know what I'm talking about, you don't need to memorize those, using the criteria we just looked at for main group elements. They are unpredictable. You have to memorize their ionic charges. And the easiest way is using the stock system. We're gonna talk about that later. So for these transition metals, we will gonna come back to that. All right. So you should be able to now you should be able to predict the ionic charge given the periodic table. And for polyatomic ion, you should memorize that. I'll post that table online so that you are able to use it to write the correct formula. Why am I bringing up that? So that you are in a position to, with the ionic charges, you should be able to write this right here. Let's see now the first class of compound. How do I write, say, one here for binary, binary ionic compounds. For binary ionic compounds, these are made up of metal plus non-metal. Binary means two, and the metals goes in first, followed by the non-metal, e.g., all right, sodium chloride, that is an binary. I can have aluminum oxide like this. It's not a number like two, but the kind of atoms are two only. I have aluminum and and oxygen. So we do not have to count and say, all right, there are three oxygens and two aluminum, and it's more than two to say binary. The kind of atoms, what is based on saying binary or ternary. Let me just give you a rule which works for writing the correct formulas. Correct formula, all right, for binary ionic. We use what we call crossover rule. This is what helps you in writing the correct formula for binary ionic. Crossover rule, all right, calls for taking into account the ionic charges. For example, sodium is in group 1 and it has a charge of +1. Chloride is chloride is in group 7 and it has a charge of -1. I'm using now the periodic table to predict the ionic charges. The crossover rule means you take the numbers, not with the sign as in positive or negative, not with the charge. I see this is -1, so it's gonna be in place for or subscript for sodium, and sodium has +1. It's gonna be subscript for what? For chlorine, and the formula here is NaCl. Behind the scene, there is 1 and 1. 1 is coming from chlorine, and 1 is coming here. 1 is coming from chlorine, and 1 is coming from sodium. We don't indicate 1 when it is understood to write it as NaCl, just NaCl. This is how the crossover rules in writing the correct formulas for ionic binary ionic compounds. Suppose the charges are different. Say aluminum, all right, Al is in group 3, +3, and say oxygen is in group 6, it's gonna form -2. So this is what I'm gonna have as my charges. The crossover rule dictates that we need to bring down the 2 here, all right? And we take the 3 down there. And this will be Al. The 2 is coming from oxygen, and the 3 is coming from what? Is coming from aluminum, and that's how you use the crossover rule. If you look at how it is crossing over, it's crossing over, all right? So you end up with the correct formulas. Point to note that is, if you can simplify further, you must do that. What do I mean by simplifying? Suppose we have, say, for example, magnesium, which is +2, and oxygen, which is -2. The crossover rules tells us that 2 will come down there and 2 will come down there. Do not leave it in this form. Don't say that, you know, I've done my work and this is the correct formula for magnesium oxide. You can still simplify this by dividing it by 2, and the correct formula for magnesium is MgO, MgO magnesium oxide. So if you can still simplify, it is okay. You can also have something like maybe lead-4, all right, with +4, and oxygen with -2. If we bring down that, this will come down there. This will be PP2 O4. The 4 is coming from lead, and the 2 is coming from oxygen. We can divide this by 2, and the correct formula for this is PPO2, and this is the correct formula for lead-4 oxide. We're gonna talk about how to use the Roman numeral later. So that's how the crossover rule works for binary ionic compounds. It works the same way for ternary. Let me just go back to this flowchart right here. I've shown you how to write the formulas for binary ionic compound. For binary ionic compound, use the crossover rule. The difference between, or before I look at the ternary, is there any question on binary ionic compounds? Binary ionic compounds? I want to shift gears to ternary ionic compounds. No, thank you. All right, ternary ionic compound is the same as, you know, the approach is the same as for binary ionic compound, except in ternary, it has, it involves polyatomic ions. This one, 2 here, let me just number it. We are in position 2 now, and say that this is ternary ionic compounds, all right? These are compounds made up of what? Metal plus 2 or more non-metals. So one at least has to be a metal and a non-metal, a metal and a non-metal. Here is, all right, here is an example. Example includes, look at this, that is a metal. These two are non-metals. I can have something like this, Na2CO3, like that. And remember, you start with a metal followed by 2 non-metal. You look, this is a non-metal, this is a metal, this is a non-metal, all right? This is non-metal right here, and this is a non-metal right here. So that's how you classify compounds as ternary. So how do you write the correct formula for ternary ionic compounds? The same way as binary ionic compound, except, you got to memorize, you got to use the polyatomic ion table. See, all right. So if you know that this has the ionic charge of -2, and maybe it is reacting with lithium, we use the crossover rule still, like that. And we have what? We have lithium, 2 is coming from carbonate, and 1 will just be silent. Don't use the parentheses. When 1 is taking care of polyatomic ion, you exclude that. It could be, let me show you where you use parentheses. It could be Ca, which is +2, and hydroxide, which is negative. This is wrong. Somebody might say that I'm using the crossover rule and I have O and 2 like that. No, this is wrong. You have to use the parentheses Ca in parentheses H O2 like that. O2 like that. You use parentheses. There is one subscript for calcium here. For calcium here, there is one coming from the hydroxide, So the point here is to keep track of the ionic charge for polyatomic ion. So basically, ternary ionic compounds consist of what? Consist of the metal cation, positively charged, and the polyatomic ion, which is basically collection or group of atoms with an overall charge. Like I said, I'll make the polyatomic ion table available online for you to use. Before we look at naming them, for the transition metals, all right, for the transition metals, there is a systematic way of keeping them or naming the ionic, naming the cations which form more than one for cations, all right? They are cations which, all right, which form more than one charged in particular. This is for the transition. Mostly they are in transition what? Transition metals. Not all of them, but common one. You need to worry about that. Use here, we use what? Use stock what? Stock. That's what we call stock system. We use a stock system, and stock system is using the Roman numeral to indicate the charge on the cation. Stock system. Stock system. You can have this. This is iron, and this is iron 3. We say that this is iron what? Iron 3, iron 2, not 3, iron 2, ion. All right, and this is iron 2, no 3, ion. The Roman numeral in parentheses tells you which species you are dealing with. All right, if it is iron 2, and then you know the overall charge on iron is +2. If it is iron 3, the overall charge on iron is +3. We have lead. Common one is lead. This is lead 2. All right, lead 2 ion. I'm assuming you know how to name the elements. I'm assuming you know how to write the chemical symbol of an element given the name. So this is for positive and lead for or ion. In case you are wondering where am I getting all these names like lead, like iron, you are expected to have learned this in the lecture. That's why it's just like I'm just giving to you that you should know. So for the transition metals, if an element is on the transition metal, you have to learn them. The stock system or the modern day, is what I recommend. I know uh, you may see in the text talking about the ferrous, the ferric, all right, the chromas, the chromic, and so forth. Those are the old way of naming ions with more than one charge. So having said that, what we have been looking at is naming them or writing the correct formula using the what? Using the crossover rule. Crossover rule. How do we name them given the formula now? How do we name them? We name the way we name the, you should be able to name. Let's start off with this. How do we name this, for example? Understand that this is called sodium what? Sodium ion. And this is, we change the ending chloride, chlorine to chloride, IDE ion. So instead of using the word ion, we say sodium chloride. You should be able to name the cation and an ion in order to name the compound. We looked at how to write the formula. How do we name now if given the word? The formula. You got to go back to the basic of naming the cations separately and reconcile to name the compound. This one, I used this before. How do I name this now? This is Al3 here. This is aluminum ion. And this two right here is oxide ion. We get rid of ion in naming this and say this is oxide like that, without using this, without using the word ion and ion. It's just aluminum oxide. Aluminum oxide is the correct name for this compound. There'll be a situation where you will, all right, or even before I look at that, this right here. Let me see how you will name this. Having gone through that, how will you name this? Use the chat feature on the Zoom to give me a possible name for the compound on my whiteboard. Somebody to volunteer the look at it, yeah. Let me help you out. All right. This is, if this is right here, this is called hydroxide. Ion. And this one right here is calcium hydroxide. Thank you. Oh, yeah. Somebody got it. That's right. This is calcium ion. and we say this is calcium hydroxide, calcium hydroxide. The point is to remember that am I dealing with polyatomic ions? Once you identify that, then you will not miss it. You know, somebody might say calcium, oxygen, hydrogen. You know, just trying to name anything the way it is, having an idea that this is oxygen. You know, you should be able, you should proceed with caution that is this polyatomic ion. If it is involved, if a polyatomic ion is involved, what is the name of that polyatomic ion? All right, and then you just move on in naming the ternary. All right. If you, again, I see common mistakes students make is when the compound, in this case, ternary ionic compound, involve that element which form more than one charged particle. For example, here, we know this one form more than one charge. There is ion 2 and ion 3. In reality, we have ion 2 and ion 3. How will I know that which one am I dealing with? How will I know which one am I dealing with? To identify which one you are dealing with, you have to look at the chemical formula of the compound given. For example, knowing that this is this is ion 2 ion, and this is ion 3 ion. All right, so we should know how to name the two particles. Those are exist. Now, how will I know which one is which? Thank you, Jerry's phones. Thank you. How will I know which one is which? If you are given, for example, FeO and then Fe2O3, all right, you cannot name both compound as iron oxide. You know, no, that's wrong. If the cations form more than one charged particle, you have to indicate the Roman numeral. This will be named iron 2 oxide, not iron oxide. No, you have to specify the charge on the cation. How will I know that it was 2? Because at the outset, I expect or I know there is positive 2 and positive 3. When I look at this compound right here, I don't see a 2 coming from, you know, from oxygen. I expect to see 2. I know the charge for oxygen is always -2. It's not going to change. But I don't see that 2 here. Where did it go? That means it canceled out. When I brought down the 2 from iron, and the 2 from oxygen, it cancel out. Remember what I said earlier on, you have to cancel out? That's what really happened here. And that is why I know I'm dealing with iron 2 in this case. And I say iron. I'll mark it wrong, or somebody will mark it wrong, or if somebody is using scan tone, you know, if you say this is iron oxide, that is wrong. It sounds correct, but based on the rules, you have to indicate the charge by using the Roman numeral. So having said that, this will be iron 3, what? Iron 3 oxide, iron 3 oxide. So you've got to be careful. Use any, you know, intro to chemistry, and I think also in the handout I gave you for this lab, you have the periodic table which indicates those elements with more than one charged particle, and you should use the Roman numeral. Common mistake I also see is not only forgetting the Roman numeral, Is somebody trying to use Roman numeral where it is not applicable? Remember, I said this is for what? Transition. Watch this. I may give you this. I may give you something like, K2 and something like that. And somebody will say potassium 2 oxide, No. Potassium always form, one charged particle, and the only time you use Roman numeral if it for transit, common transition metals which form more than, do not use Roman numeral for main group element. That's what I'm trying to say. Don't say potassium or potassium 2 oxide or whatever, trying to use the Roman numeral. Don't get confused. Just write down the notes until you understand how the Roman numeral works. With that, that takes care of, the first two classes of compounds, which you should be able to do that right here. This is the first two here, binary and ternary, and how to use the Roman numeral. Ternary and binary ionic compounds. More compounds or more information lie on this side of the flowchart. You got to be careful. Most mistakes occur in this territory right here, ionic compounds, because you got to remember, am I dealing with polyatomic ions? What is the name of the polyatomic ion? Is this Roman numeral applicable here or not? Am I using the crossover rule? Am I canceling out? Those are the things you got to pay attention on ionic compounds. Now, let's shift gears to molecular compounds. It is the easiest, and I see that, students make mistake, quite a number of students make mistake, yet it should be the easiest. Binary, we are in category 3 now here. Binary molecular compounds like that. When you first, binary means what? Binary means two. Binary means two. Molecular compounds versus ionic compounds. These are compounds made up of non-metal plus non-metal. That's when you know that you are of the ionic compound territory. You are in molecular, if I say that, it is. Two non-metals. For example, this one is carbon monoxide, CO2. This one is carbon dioxide. Just using these common, compounds which you are familiar with, you know how to name them. You have to be able to first of all recognize that this is binary molecular, two non-metals. And then pay attention to this. What I've used here is this mono and then di. You have to memorize the prefixes. If I were you, I'll start memorizing right now. It's gonna come back again in KM1. If you're planning to take KM1, the prefixes will always come back. If you have one, it indicates how many atoms. If you have one atom, one means mono, two means di. If you have three, then it's tri. If you have four, this is tetra. All right. If you have five for pentagon, penta. If you have six, this is hexagon. This is hexa, 6 of them. 7, this is hepta. And then 8 here 8, octa for octobus, 9, nona. A decade is 10 years, so you say deca for 10. Deca for 10. These are the prefixes you need to remember on the binary molecular non-metals. That is why we say carbon monoxide. We have one oxygen. Dioxide, we have 2. Here is another example right here. If I have something like 2, let's say here I'm using N2O5, for example. This will be dinitrogen, pentaoxide or pentoxide. Sometimes they say pentaoxide or pentoxide. Different texts have different ways, so that's how I'll name that. Or maybe PCl5, for example. Here, this is phosphorus, pentachloride. There's a systematic way of naming ending with IDE. In the first element, we do not use the word mono. In other words, you cannot say monophosphorus pentachloride or mononitrogen or monocarbon. You see, we didn't use the word mono in the first one here to say monocarbon monoxide. We don't use the word mono for the first element. We always use for the second element. It indicates how many atoms you have. So here, the task is memorizing these prefixes and learning the systematic way of naming the compound. And if you are given the formula, you should name. Given the name, you should write the formula. If you look at how I name this, you name as the way you name the just the element, as in nitrogen, as in phosphorus, as in any other, but you have to indicate how many they are. And then the ending changes to IDE. Instead of oxygen, you say oxide. Instead of chlorine, you say chloride. Look at how the ending changes when naming binary molecular compounds. Binary molecular compounds. Pay attention to molecular. That means non-metals. You have no business using the prefixes right here. If a metal is involved, that means you have no business using these prefixes. If you don't draw a parallel between ionic and binary, if you don't draw a parallel between ionic compounds, whether it's binary ionic or ternary ionic and molecular compounds, chances are you will use the prefixes given here and you'll get it wrong. Let me give you an example. Somebody will tell me, look, somebody will tell me that, or give me this and say, this is they say, oh, dipotassium, all right, dipotassium oxide, something like that. Thinking that, always you have to use the prefixes to indicate how many atoms they are in there. No. This is wrong. This is wrong. Why? This is a metal right here. This is a metal, and you have no business using prefixes for ionic compounds. I know, if you don't do your homework, you will not see anything wrong with that, because you are telling me, or you are telling your instructor, there are 2 potassium and you use di, which is wrong. So pay attention when you are using the Greek prefixes. And as I said, it's the easiest. All you have to worry about binary molecular compound is the Greek prefixes. There is no crossover, all right? Don't think that you are crossing over, you know, no. We do not use, you know, the crossover rule for binary uh, molecular compound. Any question on binary molecular compounds? Any question on binary molecular compounds? This is where I was on the flowchart. Real quick, this is where we are. I'm done with the binary molecular compounds. Binary molecular compounds. I want to shift gears to acids. All right, Angela, thank you. So let's see, second to last item this morning, I want to just show you how do you recognize that this is, I'm dealing with an acid. First, acids, all right? They must have, or they have to be aqueous solutions. All right, it must be dissolved in water. It must have AQ. You know, physical state, I know you know how to interpret the chemical equation, chapter 7 in Cohen's text. AQ means aqueous, dissolved. So acids are solutions. And we have two types of acid. One is, this is binary. Let me just put for here, binary acids, binary acids. How will I know that I'm dealing with binary acid? One, the criteria is it must have hydrogen, hydrogen in chemical formula. All right, and two, it must be what, aqueous. It must be AQ in the physical state. And from the word binary, it must have two elements. For example, here, HCl, this might be just binary molecular compound, hydrogen monochloride or hydrogen chloride. But if I put here, this means it is a binary acid, two nonmetals and an aqueous binary acid. And you say this is hydrochloric acid. HPR, and then aqueous, we say that this is hydrofluoric acid. HI, aqueous. This is hydroiodic acid. Hydroiodic acid. One thing I want to point out here in binary acid is, if you look at all these acids, they have two elements and two nonmetals, and they have a physical state as hydrochromic. Yes, hydrochromic. Thank you, Chelsea. Thank you, Chelsea. So this is, my brain is on overdrive. This is hydrochromic. Yes, chromic acid. So what I was saying is, for binary acids, sorry, two elements, both are nonmetals, and then the subscript AQ. You may not see AQ, but you will see the word aqueous. AQ means aqueous. My Q looks like an A, sorry about that. I'm using my whiteboard, by the way, is an iPad hooked up to my Mac computer, and it's kind of like stylus and the response. So these are AQ, 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 AQ. I know those are binary acid. Now, one thing which might not be clear in the text is, you see that hydro, always the word hydro is used in binary, all right, in binary acid. You don't use, when we look at the last class of acids, we don't use this hydro, 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 hydro. The trick is now, looking at the pattern on how you use the suffix IC, hydrochloric acid, from chlorine, chloric, from bromine, chromic, from iodine, iodic, all right, and so forth, telluric, and so forth. So those are the how you name the binary binary acid, binary acids. For ternary, all right, ternary oxy acid. This is the last class of compound, ternary oxy acids. All right, ternary oxy acids. This acid contain, they have oxygen. From the word oxygen, they have oxygen in their chemical formula. They have they have hydrogen in their chemical formula, and they have aqueous in their physical state. These are the three, you know, these are the three items I'll be checking in order to classify an acid as ternary oxy acid. Oxy acid from the word or from the oxygen. Example is HNO2 and then aqueous. I can have this HNO3 aqueous. By looking at the chemical formula, you can tell that this is a ternary oxy acid. It's not binary acid. The moment I see aqueous, I know that it's an acid. And then if I see that it is more than, more than one, or I mean more than two elements in the formula, then it is not binary acid. It's ternary oxy acid. There's oxygen in it. All of them, they have oxygen. Well, how do we name now? How do we name ternary oxy acid? I've given you the criteria by which you can identify or classify a compound as ternary oxy acid. It must have oxygen in it. It must have hydrogen in it. All right. There is oxygen and hydrogen and aqueous, of course. But how do we name them? You got to go back to polyatomic ions. All right. Pay attention to polyatomic ions. Ions. All right. I expect you to have learned the names of polyatomic ions. For example, this one is polyatomic ion. This one is polyatomic ion. You don't name them the same way. If you go back to polyatomic ion table, this is named as nitrite, ITE, and this is nitrate, ATE. The way you name polyatomic ion, you have to put them in groups. The one with less number of oxygen ends with ITE. The one with greater number of oxygen ends with ATE. There's something to do with number of oxygens and how you use ITE. This is polyatomic ion. So if you know how to name polyatomic ion, naming these acids is anchored on polyatomic ions. If, all right, for acids, if the polyatomic ion ends with ATE, this will end with OUS. This will end with ICE, ICE-OUS. So this will be named as nitrous. nitrous acid. This will be named as nitric acid. It is Taylor's. You see this IC and OUS, it has to do with the polyatomic ions. Polyatomic ions. And how you name polyatomic ion ending with ITE and ATE, you change to OUS or IC. It's not only limited to these two acids. I can also have this. Let me show you this. H2SO3 like that, and H2SO4. This is aqueous right here. This is aqueous right here. If I look at these two here, this one SO2, no, 3 with the -2 there. This is polyatomic ion 2 negative. We name this as sulfide, ITE, and this is sulfate, ATE, ATE. All right, that's how you name polyatomic ions. This ends with AITE, ATE. This is A right here, because of the difference in number of oxygen. Remember, the one with less number of oxygen ends with ITE, greater number of oxygen ends with ATE. Therefore, we change to ending OUS and IC. So this will be sulfurous, OUS, sulfurous acid. And this is sulfuric acid, sulfuric acid, changing ICE. Take note, I didn't use hydro. Remember what I say for binary? Just so that we put side to side. Hydro, 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 binary acids. Even though we have hydrogen here in ternary oxy acid, you don't say hydrosulfurous acid or hydrosulfuric acid. Don't get confused, given those in multiple choice when naming the ternary oxy acid. All you have to pay attention is the polyatomic ions you are expected to have memorized, to have learned, to have committed to your memory, the polyatomic ions. If you can name the compounds and write the names of the chemical formulas and name of compounds, you know, the world of chemistry will be much easier for you. And that is why this chapter on compounds in Introduction to Chemistry is titled Language of Chemistry. You can know the compounds, and then you can speak the language of chemistry. With that, I want to stop here and take question if you have any question. Any question? If there is no question, I'll just share the data sheet for the day. What you need to do is pretty straightforward. I covered a lot of material, which I believe it will help you in completing the, you know, the data sheet. This is basically, you know, what you need to do. You're gonna read the background, and mine was comprehensive. My notes was comprehensive. How you name the polyatomic ion. What I want to show you is how do you name or what you need to do in every section. All right, in every section. What section am I talking about? All right, here in part A. All right, let's see part A. You see, this is the lab report right now. Name the following compounds. You know, all of them, you know, it's a mixture here. These are ionic compounds. Some of them, you have to use the Roman numeral. Some of them, you do not use the Roman numeral. So given the formula, you should be able to write here. If I look at A2, this involves polyatomic ions. And I said I'll share the polyatomic ions table and put any other resources on Canvas announcement section. I did last night, but I forget to click save. So when I check on the announcement today, I couldn't find all the resources I put on Canvas. So here you should learn the polyatomic ions involved. Now, given the name, are you able to translate to chemical formula and still using the crossover rule? You know what Roman numeral means, okay? I don't want you to miss that concept. Now, given the formula, are you able to write the form the name? If I look here, section C, you have binary molecular compounds. All of them, you know, they are non-metals. Everybody knows carbon dioxide, not carbon 2 oxide, no. So you have to remember that. So given the formula, you should write the name. Part D is, given the chemical name, are you able to write the formula? It's easy, right? It's easy. Just remember the prefixes, what it indicates. Part E, even though it is optional, I want you to do. This is what we just talked about. If I see here is there is ternary oxalic acid. There is a polyatomic ion involved here. How do you name that? These two here are binary acid. How will you name that? These two are ternary oxalic acid. How will you name that? And then here you'll have to write the formula given the names. And that will be it for this lab, all right? This is due next Sunday. There's a periodic table here. You know, it's not complete with the elements, but it's just giving you the ionic charges. But in the exam, you should be able to predict the ionic charge for main group. These are the A's, which, you know, it's coincide with that. You may see some blank space. But for this exercise, you can use this to see which element has more than one charge. And of course, polyatomic ions here with their names. Remember, polyatomic ion act as if it is one element, that the overall charge here, you cross over. Remember to use parentheses where applicable. Remember to use the parentheses where applicable. For example, I can put here parentheses and the 2 coming or 3 coming from whatever element I'm dealing with. If there is no question, I will, all right. If there is no question, I will stop here, and there will be a quiz on what we just went through. I want you to read again relevant section in your text so that when you take the quiz on writing and naming compounds, it will be easier for you. Otherwise, thank you for joining in this morning. Hope to see you on Monday. Please send me an email if you have any problem. I'll try to either schedule a Zoom meeting or respond via the email. Other than that, be safe, have a good morning, stay healthy. Thank you. The class is dismissed. You can leave now.